Oh, the audio is running too. That's good. Make sure the mics are on. Amped up. All right. Let's see. Jonathan, can you hear me?
Yes, Professor.
Okay, good, great, thanks. All right, so any questions on the homework? Have you guys looked at it? Yeah, tonight, I guess. Hopefully, I mean, it'd be good if I guess I email one guy, but like if the grad students could kind of organize the homeworks, that's like the ideal situation, you know, like corral the undergrads, but anyway, that would be an ideal world. All right, so let's see. So I got these two things. I wanted to get to slide number. I wanted to finish off this business. I think it's in this. Yes, we did RG, and then we got to this business. We did that. I should just remember what slide number it is. But then we got to this, right? And I said, all right, so yeah, so this is where I'm going to start, I guess. Although it's the other set that I want to go through today, but I'd plan it. All right, so I said, like, you can take the oops, this guy's not in here. Okay. So you can take the divide function, which you get by integrating. So you integrate, you stick in the NL squared for the R, for the difference of the R, so into the 1/2 L, the difference in the R's, and then you get this function out of that, out of this double sum. Right. So this is the exact function for a Gaussian chain, right? And so usually you have like the correlation function as a Fourier transform, and you get this. So like if you have a sphere, then it's the Fourier transform of the basically the spherical shell position, gives you the density of the position, then you Fourier transform that and you get the scattering function, right? So, but in this case, so this is the Fourier transform here, like exponential I would be like sine plus I cosine. So this is a sine wave. So this is a sum of sine waves of wavelength q dot r, right? So you can convert from R space correlation function to Q space scattering function, and the Fourier transform is a transform of that. And you can do a reverse Fourier transform on that to get to the correlation function, right? So but this function you can't Fourier transform, like it's not Fourier transformable, you know. So you can calculate it analytically by sticking in, by saying this thing only has a value when the two positions of the chain are there, right? So then you can plug in, so you can get this exponential IQR only has a value when Rm and Rn exist in the chain, and that happens when it's NL squared. So you can plug that in and then do this double sum and get this function out of it. Okay, so but it doesn't work exactly. It doesn't work if you have like an expanded coil, but you can get an integral function. That's an exact function if it's an expanded coil. Anyway, so because you can't Fourier transform that, people, I guess, didn't like it or something. And then Ornstein and Zernike in a footnote mentioned, and also this thing in the limits, it matches like at high Q, it's Q to the minus 2, low Q, you get Guiney's law. Like if you do the extrapolation of that. And then Ornstein and Zernike mentioned in a footnote that this function is like a useful function because it had for random systems, not for polymers. Like if you have, they were talking about when you have just a mess of objects that are floating around, and kind of what's the correlation function for that? Well, it's just a decaying curve, like a decaying exponential curve, in fact. So you can Fourier transform that decaying exponential, you could get this. They didn't say that, just said this thing would be good. But later, I mean, people kind of tried to Fourier transform this, and you get this function, right? So this function's got some problem because if you think about it, the things are randomly distributed in space, right? So if you go forward in R or backward in R, you see the same thing because it's random. But this function isn't doesn't go forward and backward like that. It's got a negative R. So the backward and the forward aren't the same. In fact, the backward one goes exponentially increases. So this is a non-physical correlation function. Right. So that's one problem with this. The other problem is, you know, the exact solution. It's this Debye function, and you can compare the two limits, like the high Q limit for the Debye function is this thing, the high Q limit for this thing is that thing. That would indicate that this correlation length, which is kind of a mystical number. I know they said that things are randomly moving around. There's an average separation distance of the things in the system, like a liquid state, right? So that average separation distance is loosely defined as a correlation length. There's no exact calculation. It's not a real number. It's just like an idea. Like, yeah, there's kind of an average. And it comes from the idea, like when you shoot a beam of X-rays through a liquid, you get a hump. You know, so like the atoms are kind of located at some distance, a correlation distance. That's kind of you could say it's the middle of that hump, the amorphous halo, right? So there's not a diffraction peak that has a real position, and you can do Bragg's law to figure out what it is. It's just a hump, you know, and it's not even really a Gaussian hump. It's kind of a log normal hump. You know, it's got a tail to it. So this asymmetric hump, and the peak of it could be like thought of as some average length that things are separated. But see, it's just fluffy. There's no real definition of this number. If someone asks you what's the correlation length, you have to say it's fluffy. You can't say it's anything because it's not something you can pick up, right? So nonetheless, this function you can compare with the Debye function that's got exact answer. And then you find out that it doesn't work for polymers because you have the two solutions at high Q and low Q give you different relationships for Rg. In other words, the high Q and low Q both depend on Rg in the Debye equation, which is the exact analytic calculation. And then this doesn't work, like it doesn't give you the same answer. So the two curves you get from these two functions are different, meaning that this correlation length is meaningless, except as a fluffy idea. Okay, so it kind of has something to do with Rg, I mean, you could say, but you don't know exactly what. So anyway, so then that led to a family of equations. So once people realized you could use, and this is the same, so Debye loved this exponential, non-Gaussian, just an exponential decay, like the Debye screening is the same thing, right? So in other words, it's going to be the Debye, this correlation length is replaced by the Debye screening length. So he loved the exponential, everything he did. If you look through all the stuff he did, it always involves this function, you know, so he kind of gravitated to this thing for some reason. But anyway, so you could say like the Debye-Beaucage function will give you like, basically they call it Perot's law, Q to the -4, which is for a solid object. And if you throw it in this format, which is kind of reminiscent of this so-called Ornstein-Zernike function, which again was a footnote. I don't think they intended this to be named after them, and they probably would be upset about it, you know. So anyway, so this function, though they did name after them, Beaucage kind of came up with this, and then it's the same function as this, except get rid of the R, and you come out with Q to the 4, which is like Perot's law, Q to the -4, which is this would be like the surface to volume ratio at high Q, the G thing here, but this again, like doesn't match reality. Like there's no relationship between, this would be the n squared capital N, like the concentration times the number of electrons, this G, and then this thing is this fluff number, right? So this equation also is bogus. It also has like a negative, not symmetric function about 0, right? So this came out, this has been around forever. This is around 1960s. And then this is like in the 70s, this Tubner-Stray function, where they invent like two arbitrary things. This having two things that have different signs will create a peak. This is totally empirical, right? This is just like freewheeling. You know, it does have a Fourier transform, which is this weird thing, which has our non-symmetric friend here. And a symmetric thing, it's okay, you know, but so basically this is kind of a combination of this and that. You get something that's a combination of the two, they were kind of happy with it. So you'll see this referenced all over the place too. This bogus, that's bogus, and then this is like super bogus, because even the two parameters, there's no reason that one's positive, one's negative. This is used to fit peaks in micellar systems, so things get worse. So then Sinha, who's a guy at Argonne, and this is from like 10 years later, like late 80s, so there's no scattering function for random fractals like dust particles, so the Sinha function does that. And again, it's got this friendly exponential thing. And instead of 1 over r, you put r to this fractal dimension thing, and you end up with, at the high Q limit, this goes as q to the minus df. And at the low Q, you get something like Guinet's law, but it doesn't match. You can't actually get Guinet's law out of this. The high Q does give you a power law decay. It kind of looks right, but again, the numbers, the correlation length doesn't mean anything. It's just like a garbage can size parameter that people are using loosely to throw around, right? So it's scary. Anyway, so there's a whole family of functions based on that Ornstein-Zernike function, right? So anyway, so that's one thing. I mean, I kind of mentioned that already, but I mean, just say it a little bit more. Anyway, so that, let's see. So that's one part of this thing. And then the homework this week's on this business of if you increase the concentration, right, of the system. So these are all like a single polymer coil isolated, like dilute below C star, below the overlap. So you just can see one of them, right? So when you increase the concentration, this thing happens that you can't see the coil anymore. The coil can't be picked out of this, like you can't find a sheep in the herd. Right, so you just have one sheep, that's our dilute, and then this is above C star, right? So you can't see the coil. So, but you see something. So the thing has this, and that's called the correlation length, right? So basically the size scale here that comes out is like this network. Like how big is the network here? What's the distance between chains and the mesh size of the network, basically, right? And as you get to higher concentration, the mesh size is smaller. This is 1 over size, so it kicks out to the right, right? And then below that, you see just uniform, right? So below that size, you see uniform. So this is like, if you think about this like a fabric, okay, so if you have something like this, like a fleece or a tissue or anything non-woven, like non-woven polypropylene they use in diapers and things, so something like this. It's a mesh of things. Same as a polymer in solution. It's kind of a mesh of things. It's got hardcore repulsion, so there are interactions in it, right? So the things interact with each other, but it's not like this, like a woven fabric where you have a structure to it. So the fibers are forced to be in a certain position, either mechanically in the case of woven fabric or by charge, like if they're repulsing each other by charge. So if you have like colloidal silica spheres or colloidal polystyrene, you can make them nano, kind of 100 nanometer size. Those will have surface charges, they repel each other. So you can have something like a distribution of them that's kind of random, but they're organized on a local scale. So you get a peak in the scattering function versus this, there's no peak. So scattering can tell immediately, do you have specific interactions or do you have mean field? So this thing's called mean field. So you'll see like over and over again, we're assuming mean field, we're assuming mean field, we're assuming mean field. That means it's probably not going to work for proteins that have charge on them. They're repelling, right? Unless you have a salt concentration that screens the charges. And it's not going to work if you, from this picture, you can't tell if that's mean field or if that's specific interactions. So the best way to tell is shoot neutron, X-ray, or light through it and see if you get some kind of humps. And if you get humps, well, there's 2 reasons you can get humps, but basically if you get humps, you probably have specific interactions and this kind of thing won't work anymore, right? So in that case, you need to use the Ornstein-Zernike theory for correlations, not that Ornstein-Zernike function for fitting the scattering. They're 2 separate things. And this is why, even though Zernike won the Nobel Prize for this microscope, confocal microscope, they should have given it to him for this, but because Nobel Prize, you have to do something to win it. Like it has to be something that's functional for society. The idea is science helps society somehow. Or this function doesn't really help anyone do anything except say like why, like how do you fit this curve? Like how do you understand interactions and systems where they have this kind of thing? So the issue is like you have a that once you get to above the overlap concentration, then you have like in the B2 we're dealing with here is like the binary interactions. You have the binary interaction, but here you can't ignore like the higher order terms in that viral expansion. Like there's ternary, there's quaternary, there's all these other interactions, and it's going to go to like infinity, and that's going to affect how it forms like a FCC crystal. Like you can see the hexagonal lattice here, right? So anyway, so basically no one knew how to do that until like 1960 or something around that time, I guess. And the Ornstein-Zernike function was kind of how to do it, and it's kind of heavy in mass. So the end result is that there's a binary function, and then so the total function is going to depend on like this kind of interaction of the things. So the binary interaction is going to be influenced by other binary interactions, which leads to give you the whole interaction of the thing. So you have to consider how the binary interaction here is influenced by the binary interaction there. So it's a function that depends on itself, right? It's a what do they call that? I just forgot. But anyway, it's a function that depends on itself, which means that if you have a function that depends on itself, a recursive function, right? It depends on itself. So this C of R is the gamma of R. Like they're the same thing. It's an integral of how the things interact with each other to give you the total thing that happens. So it's not a simple thing like so in order to solve that, so it's redundant. It goes back, you can't solve it because you don't need to know the answer to solve it. You can't solve it without knowing the answer. So basically they call it closure relationships. You assume something to say, how does the final result relate to the binary interaction? We can solve it. And you can kind of solve this. And there's various ways to do that. One's called the Born-Green approach, which is simple. One's called the Perkis-Yevik approach, which is really complicated. Supposedly this is better, but they kind of give the same answer. So anyway, the answer is you can develop a function that will describe this behavior. So the way this works is in the scattering, you have the form factor and the structure factor. So the form factor is what is the thing. So in this case, it's colloidal spheres. So this is the sphere scattering function. Unfortunately, this function, so if it's a polymer coil, there's no order to it. It's just the Debye function, the decay function, right? It's like flat and then it goes down, right, in a log-log plot. And for a sphere, though, because the sphere has a perfect size, so once this R vector that we're talking about gets to the edge of the sphere, then there's a discrete cutoff. And because of that discrete cutoff, that's like a spacing. So that it sees that just the way it sees planes. So it gives a peak. It sees that discrete cutoff. So basically, each one of the peaks from this function will be at 2 pi over the diameter. And the next one will be at 4 pi over the diameter. So it's fringes. You get a fringe pattern from this function for a sphere, right? And you can get the radius, the diameter of the sphere from that function. So that makes things complicated. You have that thing here, and this thing also has the correlations of the spheres, which is at almost the same size, right? It's almost at the diameter. It's a little bit bigger because there's some space in there. So basically you have those two things in there. So it's a little complicated to analyze these things, but basically, I mean, if they're spheres, if they're polymer coils, and it's easier actually, right? So or some kind of fractal thing, it's easier because you only have one kind of correlation in it. The thing from the structure factor, which is this is the correlation function. That's one form. This would be the exponential I if you have symmetry with the correlation. So you get you I squared because you have the symmetry that's symmetric about it. It isn't like there's a direction to it. So this is a non-directional Fourier transform. It's R squared dr to get full space 4 pi. Then this thing is like the exponential I integrated for randomized in all directions from the center. So anyway, this is a Fourier transform, even though it doesn't look like it. And then that gives you the Fourier transform of the correlation function gives you the scattering. That's the idea. And the scattering here is a structure factor. So if you want to get this, you measure the measure intensity of your semi-dilute solution, so above C star, and then you measure the dilute to get the form factor. What is the thing? So you dilute out the spheres, you get the sphere function. Then you divide IQ that you measure for the semi-dilute by the dilute, and then you can get just the structure factor. So you do, and then you take the concentration of the dilute, so the ratio of the concentration of the dilute, the concentration of this thing. So you end up with this function to get S of Q. So it's easy to measure. You measure the dilute, you divide it by the concentration of the dilute, because that's a prefactor. Measure your semi-dilute or concentrated and divide it by the concentration. Then the ratio of that gives you just the S of Q, which you can fit with this function. You get the G of R from that. You get the G of R from this Ornstein-Zernicke with some kind of closure relation, right? So it's complicated. This has little to do really with polymers in a sense, unless you put charged particles into the polymer. You want to know where they are, things like that. Or if you're looking at protein structure or something like that, charged chains. So, but the reason to mention it is because every time you're going to see polymers, you're going to say mean field. So why are they saying that? You know, why do they say mean field? Fourier-Huygens equation is a mean field equation. Like, why are they saying that? That's because they didn't want to distinguish it from this, right? From this kind of correlated system. They're saying it's a mess, basically, when they say mean field, and we don't need to worry about any of these things. No specific interactions. It's just one number. The chi parameter is going to decide it. But so one other thing is that, so here we say, like, so we plot intensity divided by concentration, right? Then that drops because of the RPA equation, whatever that is. So this equation, so that by that, so as the concentration goes up, this is negative, that makes it drop. So B2 makes it drop. If it's miscible, B2 is positive, and then this thing will drop. Okay, so in the miscible, as you increase concentration, this drops. The rate of dropping is chi, or B2, second Vero coefficient. How fast it drops in concentration, this I by C gives you that. So the thing is, when you get to this system, right, so it's completely different out here. That's the details of the structuring. This thing has no structure, that does. But see, the shirts look the same once you zoom out. You can't tell if it's a fleece or a sweatshirt or if it's a woven shirt from far away. It's the same thing, right? And it's only going to depend on the how dense the fibers are in it. That's it, right? And then also how the fibers like interact with each other tells you how it kind of the texture of it in a sense, right? So basically, at low Q, these two things give the same answer, even though these are completely different. High Q, at low Q, this, if you plot intensity divided by C, that thing's going to drop as the concentration goes up if the things are miscible, right? And from that, you can get a B2 from this system or from that system, as long as you extrapolate to 0Q. So 0Q means, is it look at the shirt, can you tell from far away, is it woven? Is it like a t-shirt's woven, or is it like the fleece or whatever? You can't tell, right? So you just can say that you get the B2 from that. 1/5 B2 gives you that thing, right? So that's kind of, I think that's kind of all. Oh, not all I want to say about this. All right, one other thing. So this is, all right, so the Zim plot, right? So you'll see the Zim plot and people ask you about it. And if you run a GPC, so GPC, there's a column with a gel in it, and you put super high pressure on it. I think you're putting like 500 atmosphere pressure or something on the liquid to force the polymer solution. So you put in like a 10 mg per ml solution in, and you crush it with this pump through a little tube. So it's not a huge pump, but you force it through the gel, right? So the big polymers, and you're forcing it through at a very low flow rate. So there's a diffusion of things. They're moving KT, really, exploring this gel with KT, but the pressure is pushing them through at the same time. But mostly they're exploring, like randomly exploring. Well, the big ones, and the more things are to explore, they spend a lot of time looking at it, you know? So, and the big things, they can't explore as much in the gel, so they just zip through. And the little things have a lot to look at because they can go into every little crevice. So they spend a lot of time there. So the first thing that comes out is the huge things out of this thing. So you inject at a certain time, and then you have some detector, like an IR detector that says like, oh, there's something there. And it spikes whenever the big thing comes through, and then spikes when the little thing comes through. And that intensity is proportional to the amount. So you can say like the amount versus time, and the A would be big and B would be small. That's the idea. And the solvent's the smallest thing. It comes out at the end, and then there's some tracer thing at the beginning, I guess. I don't know what V naught is. And then you're going to invert that through a plot that relates time to molecular weight, because this dependence is due to molecular weight. So you put some standards in and you get that curve, and then you can convert it to amount versus molecular weight. And that's a polydispersity. That's the molecular weight distribution curve, right? So when you do that, this thing is fractionating your material so that you get like almost nothing. Each time step, when you take a picture of it, there's nothing in it. It's like zero concentration. It's just a small amount. So if you look at this, right? So this is what's called the Zim equation, right? So this end. So if you take Guinier's law, and you take intensity is e to the minus q squared g squared. If you take 1 over intensity, or concentration over intensity, so g's concentration, then you get exponential positive, right? And if you expand that for a small q, you get 1 plus this thing. So that's part of the Zim equation, just Guinier's law. 1 over Guinier's law, it's plus because it's 1 over intensity. So 1 over exponential minus exponential is plus exponential. So that's part of the Zim equation. It's concentration over the here it's called S, but basically this is P in the other equation, the form factor of the Polymer chain. Sometimes it's called structure factor because if you look at each Kuhn unit as a thing that's scattering, this is the organization of the Kuhn units. So it would be like structure factor. So when we talk about polymer scattering, the structure factor and form factor flip depending on your point of view. Your point of view is the Kuhn unit, then it's a structure factor. Your point of view is how do the coils arrange, then that's a form factor, right? So it depends on which position you're sitting in. And this part is the viral expansion. So the zero Q is going to be the derivative of the osmotic pressure with concentration, which gives you the viral expansion. This is B2 times concentration, which would have been concentration squared. This is the first number in the viral expansion. That's the concentration term. Derivative gives 1 over n. So you have this term and that term. So if you say, so you have like coming out of the GPC, you have like 3 detectors, 3 optical detectors, and your concentration is 0 because it's fractionated down to nothing. You put in 10 megs per ml. By the time it comes out, it's like a billionth of a meg per ml or something for each time step because it's been fractionated in that column. So for each time step, your concentration is 0. Your concentration is already 0. So you're already at 0 concentration. And then if you have 3, you can extrapolate Q squared to get to 0. So you can do it. So this is the Zim plot's a double extrapolation plot. Q squared, so Q is 4 pi over lambda sine theta over 2. If you square it, it's sine squared theta over 2. You forget about the lambda part because you're just doing extrapolation here. And then, or you figure out the lambda part later. And then because you're changing concentration, also you throw in a concentration term. And this term is linear in concentration. So this is Guinier's law, and this is just slopped in for the 0 Q limit. So it's got a concentration dependence. It allows you to do a double extrapolation. So you get 2 curves on one. And you plot concentration over intensity. Delta R is the intensity. And there's a K factor, some constant front. So that's the Zim plot. It's a double extrapolation. You do a bunch of measurements in concentration and an angle, and then you plot it like this. And the slope of this one gives you Rg, and the slope of that one gives you the interaction parameter, B2, right? And if you take it to 0 concentration and 0 Q, so you do a double extrapolation, the green dot gives you the weight average molecular weight, which your fractions here in the GPC are monodisperse because you cut it down because of the size exclusion. You've cut it down to just one chain in that thing. So it doesn't matter what moment of the molecular weight distribution you get, they're all the same because there's only one fraction, it's only one chain. So in that case, weight number, Z average, all the moments, like the first, second, third, fourth, fifth moment of molecular weight, if there's only one chain there, they're all the same number. Right? So there's only one number you get out of, even though it's a weight average, it comes out of light scattering, it'll be the same as there's a viscosity average too, you get from viscosity. So basically they're all the same number. So any technique you use to measure molecular weight is going to give the same number because it's monodispersed once it's gone through the column, right? So it's basically, you need 3 detectors, you can extrapolate the cube part, then you can get the molecular weight, which is what you're trying to get out of this GPC, is this molecular weight distribution. That'll give you an absolute molecular weight for the thing. That's not based on standards, that's an absolute number. So basically, if you have a light scattering detector, so usually they'll have like 3 detectors, index of refraction to just get how much, and then light scattering, you get an exact molecular weight, and then viscosity gives you an exact molecular weight too. So you have 2 measures of molecular weight, and you also have the amount from the IR being from the IR measurement. So anyway, they say that's a ZIM detector, but it's kind of cheating in a sense because it's 0 concentration measurement, right? So there's only 1 concentration in that measurement, and that's the most common application of the ZIM plot is in the GPC, because it's just inject the stuff in and it spits out the answer. Otherwise you're going to go to a light scattering machine, you're going to have to do a lot of measurements in concentration, and in Q's easy, but the concentration is kind of painful. And then you finally, but you're going to get 2 numbers out of that, the interaction, the second Bureau coefficient, and then you're going to get RG out of it, and you also get the molecular weight from this measurement. So anyway, that's kind of where this is going. That's one thing that I wanted to quickly just mention. And then the correlation thing, what else is in here? Seems like I skipped something. This isn't on the homework, right? Part of this is on the homework. This business is on the homework, but to get the chi parameter. So that's using the RPA equation, right? It looks like the ZIM equation. So ZIM equation was like 1960s, 50s, or 60s. Bruno ZIM was at Brooklyn Polytech. It's like after World War II. So during World War II, MIT became really big because of radar. They invented radar there, and so they got a ton of money. But before that, so there were a lot of refugees from Europe that came to Brooklyn, New York, Jewish mostly, but others also. Anyone that was fleeing the Nazis, So anyway, they all ended up in Brooklyn, New York. So, and some of them were really smart. Some of them were like the top scientists from Europe. They went to Brooklyn Polytech. So Brooklyn Polytech became the best school in the United States by far. So Bruno ZIM was one of them. He was a guy a guy named Herman Mark. So Mark Hoink equation guy, right? They were both at Brooklyn Polytech, and a lot of people were young, like there's like the guy I worked for PhD was in Brooklyn too. And in his class, there were 4 Nobel laureates in his high school class, right? So there were a lot of smart people, and they were also eager to like move on. So and so that's just the Nobel laureates. Who knows how many were like famous scientists and stuff too, So anyway, so basically Brooklyn was like a big place. ZIM was there, and he invented the ZIM plot there. And my guy, the guy I worked for, Stein, actually worked with ZIM for a little bit as an undergraduate. So there were, I guess it must have been a pretty interesting place to be around then, I mean, the 1940s, late and near World War II and just after, I think there were a lot of things going on. Actually, that was before, because he was already in polymers during World War II. He went to like England and stuff. So anyway, no, ZIM stayed there. The guy I worked for, Stein, went to England. He worked with somebody there for IR stuff. But anyway, he worked with deuterated, but at the time, so deuterated polyethylene, but basically that was coming from Norway. Like they were trying to build the bomb, nuclear bomb, atom bomb, right? So they were in Norway was where they had all this seawater, and they were doing so anyway, somehow they got deuterated stuff in England, So he was doing IR, so deuterium weighs twice as much as hydrogen. So the peaks shift, because there's vibration of the bonds. When you double the mass, the vibration like gets lower. It's like a bell that weighs more, it has a lower tone. It's basically if you deuterate some components that change, they can find them in IR easily, because the peak will shift by half the wavelength. So anyway, so he was doing that, and the deuteration process and having deuterium was linked to the war effort, because they were trying to make atom bombs. The deuterium was somehow linked to that. It's I don't know exactly how deuterium's related to atom bombs. I think it's like it's a shielding or something for radiation or something. I don't know. Anyway, it was all tied together with the war effort, World War II. Crazy things were going on. Anyway, Zim was tied into that too. So it's historic stuff, but still, like, you probably need to know what it is and things. This business. All right, that's it for this thing. I don't like at one point we had someone in the class that was doing this stuff, so I went through this in detail, but basically that's all I want to say about that, because this isn't really important to polymers much, although you'll hear polymer physicists talk about this, and they like Ornstein-Zernike, and they use the Ornstein-Zernike function all the time, this bogus function, you'll see it, and you'll see it in this paper they use it. Not only that, they use this function. So they have the low Q part in the paper, it's just gunk, right? Which is appropriate for the Ornstein-Zernike function because it was invented for gunk. It's like, oh, we don't know what's going on. There's this function that could fit it. That's literally what they say in a footnote of a paper. But then he's using it also for the polymer chain at the high Q. So he just randomly puts in whatever dimension he wants here and just says that fits the gunk. And then if it's 2, it fits the polymer or something, So it's not unusual to do that. It's just wrong, So anyway, that's that business. So this is in the paper. But anyway, that isn't what you should remember Ornstein-Zernike for, all right, so let me get out of this thing, go to the other thing. So we got, let's see, this guy. Yeah, so what I really wanted to talk about today, which you get a few minutes, is this going to the hydrodynamic radius business. So anyway, so there's the 2 numbers in this plot, right? One's RG, which we kind of know roughly. Comes from Grignier's law for the most part, but people calculate it also. And then there's this hydrodynamic radius. So like, what is that? So that's basically from Stokes' law. That's going to come directly from Stokes' law. So 6 pi times the viscosity times the hydrodynamic radius gives you the drag coefficient. If you measure the diffusion coefficient, use the Einstein-Stokes equation, and that's how you get this thing, right? You look at the transport properties. So you find out what's an equivalent sphere to whatever the thing is. So I have a polymer chain, I'm going to model it as a sphere, right? That's the idea. So this is the spherical radius that would give you the same drag coefficient. So it's a transport number. So it isn't appropriate to average the number itself like it was with RG. We're actually looking at the moment of inertia of the mass, it could be weighted by the electron density for X-rays, the neutron cross-section for neutrons, or the index of refraction for light, right? So the weighting factor is going to be different, but basically it's a moment of inertia. Like you find the center of mass, find all the points, find the square of that average, and get the radius of gyration squared, right? So if you do polymer coil, it ends up that the separation distance is NL squared, so you can do that deal with this thing, right? Whereas with the hydrodynamic radius, you're looking at the transport, so you're getting the average transport, right? So if you're going to do like the average, so it's like a velocity almost. So you want to find, if you're going to drive to Columbus, and like half the time you're going to go 30 miles an hour, and the other half you're going to go 80 miles an hour. So what's your average velocity? You use what's called the harmonic mean to do that. So you take 1 over 30, 1 over 80, and you find out it's going to be something like 40. Your average is going to be something like 40. It's going to be very close to the small number because it's an inverse sum. It's going to be the sum of 1 over the speed plus the sum of the other speed, 1 over the other speed, and then take 1 over that sum. Divided by 2. That would give you your average speed to get there, right? So if you're talking about rates, which is what you're talking about here, the diffusion coefficient, you end up with this 1 over thing. you know, for the harmonic mean. So if you have like the arithmetic mean, like say you had like 2 and 6, right? And the arithmetic mean would be 4, right? And if you have 2 and 6, there's also the geometric means would be like 2 times 6 is 12, and you take the square root, which gives you something like 3.5. And if you take the harmonic mean, it's 1 over 6 is like 0.2, and 1 over 2, which is 0.5, so 0.7. And you take half of that would be like 0.35, which is kind of like 3. So it's much closer to the 2 than it is to the 6. Whereas the other one's right in the middle. The arithmetic is right in the middle. Geometric's kind of a little bit closer to the low end, and the harmonic is near the low end. Right, so you get, because it's 1 over, it weights the small things more than the big things. Anyway, so this is a 1 over situation. So when you average this thing, you average the 1 over the distances, you sum all the coupling. So here you're summing all the coupling of the 2 straight up squared. This is sum of that, and it's not the square, it's a sum, just the sum. So the number's lower, bottom line. So favoring the small things. Unless you have a solid object, and then the number is higher. Because we know the radius of gyration, the square of the radius of gyration is 3/5 of the radius of a sphere. Right? And then, so the square root of 3/5 is like 0.77. So the radius of gyration is 0.77 of the radius of the sphere. The hydrodynamic radius is the radius of an equivalent sphere. It's actually the radius of the sphere. So it's higher for a solid object. Right? So this ratio down here is going to be like 0.77 to 1. It's 3/4 of it. Whereas when you go here, because it's an inverse sum of all these positions, this number is much larger doing the straight square. And if you do that inverse sum is weighting the small things. It's kind of, so that's useful because then you can take the ratio of RH to RG. If it's less than 1, you have some kind of fractal thing. If it's a bit larger than 1, then you have a solid object. So say if you want to study protein folding or something, this is going to be really useful to see, like, do I have this fluffy thing or I have a solid thing? You can just tell by doing the 2 measurements, right? Or calculating it or whatever you want to do. So I said, kind of says over here, right? So whatever different conditions, you can get different numbers for that. Theta conditions, so this kind of signature numbers that you look for. You never get exactly those numbers, you know, so, but anyway, so anyway, this is called the Kirkwood-Reisman theory. This equation, this kind of approach. It's a little bit more complicated than this. This is simple for polymers, but the actual one's like an integral of the diffusion coefficient for different. Anyway, so the actual one's a little bit like significantly more complicated than this equation, but it's hard to understand. But basically, like if you ask that chat GT or whatever, what's the Kirkwood-Reisman's, it'll come with some crazy thing. You won't be able to understand it. Not that you can understand this, but anyway, Kirkwood was at Yale, and so was Onsager, who won the Nobel Prize. You know, Kirkwood, and they shared like offices or something. They were like next to each other, and obviously 1907, 1903, they were like the same time. But he died in 59, so he lived like 52, right? Like he died pretty young. This guy lived till 76. That's like significantly longer at that time period. You know, 73 years. Still not a huge lifespan, but I think Onsager had some stuff in World War II where he was like dragged around somehow. Anyway, so it's kind of like the graveyard. They're like buried next to each other. They were friends, you know. So basically, Kirkwood was buried first, and he put down like everything he ever did, you know, on his gravestone. Then Onsager, this is kind of famous in science, I guess. So Onsager just said like Nobel, like he never won the Nobel Prize, and he wanted to. You know, he won every other prize. Couldn't get the Nobel Prize. He died too young. You have to be alive to win it. And he died at 52. So like you'd have to be like 60 maybe, you know, like have done whatever he did. Anyway, he lived long, so he won it. But he says like instead of, and he knew this gravestone was already there, so he put like Nobel laureate star, etc. You know, just the kind of as a joke, you know, for the. Anyway, so it's kind of interesting. And then this paper. So Stockmeyer's a guy from Dartmouth, you know, he's like the polymer guy at Dartmouth, he's dead, I think, but basically he published stuff about RG-RH ratio, this macromolecules 80 paper. You know, lists every possible if you want to see like where that ratio, like what you could possibly do to figure out these things, people overindulge essentially, basically he goes through every possible star polymer ratio, whatever, as if you're going to tell the difference between 1.5 and 1.73. Like you're not really going to measure that because the things are probably dispersed to begin with. So anyway, so how do you measure this? So the next, so what it is, let me get rid of this thing. Figure out where it is there. So anyway, so how do you measure it? So it's simple to measure the hydrodynamic radius. This is called a Uberhold viscometer. I think I don't remember how to pronounce it. It's basically a capillary viscometer. We have a bunch of them in the drawer upstairs. Yeah, it's not really worth looking at, but these are popular in chemists, like people synthetic chemistry, right? So because it's easy to do, so you're gonna put polymer solution into this thing, right? And you start out first, you run the solvent through, so you get the solvent viscosity. And then you're going to put your polymer solution in. So you put in, like, not fill it all the way, so you could dilute it inside the thing. It makes it easier. So then you're going to run like 3 concentrations through it, and then you're going to get the viscosity using Purcell's law, which gives you that the basically the flux, the Q is going to just be proportional to the time of the thing. Whatever, somehow you can get that out of this, but basically the flux through this is going to be proportional to the time, and then from that you can get the viscosity out of the thing. So I think that's better described here somewhere. Let me see. Not there, not there, not there. Maybe it isn't. I thought it was one of these slides had Purcell's law and how you do that. But basically it's pretty simple to get the viscosity of the solution. So you can get the viscosity of solution from that, or you can get a Couette viscometer. So this is just showing the bob. So there's a bobbin cup viscometer. There's a cup that goes over that. You put your stuff in, the spins, that reads out the viscosity. It's like the torque gives you the shear rate, and then the speed is the shear rate is the speed, the torque is the torque on the top, and you get the viscosity out of that. That's the simpler way to do it than this. This thing costs like, I don't know, $4,000 or something. I don't know. It looks simple. Basically, they can charge whatever they want because you're not going to make it yourself. This you can make yourself. Anyway, this will just spit it out. This thing also, like, the viscosity is going to be exponentially temperature dependent too. I have that in here somewhere. So basically, you want to have control. Oh, that was it right there. So you're going to have this kind of temperature dependence. So you need to control the temperature carefully. The viscosity changes a lot with temperature. So with the Couette viscometer, it's usually got temperature control in it. So you have like the cup is actually insulated, and it's got water that runs through it. So you get isothermal, and you can ramp temperature and get that activation energy for viscosity, like the exponential argument thing. It gives you like the energy that it takes the atom to flop over another atom type thing. So anyway, so what do you do with that number? Well, we saw like if you measure the viscosity of a solution, and it's going to go like it's entangled, and then it's going to go, well, you get the solvent viscosity, like it's just going to go to flat out reach the solvent viscosity. So you don't have any information about the coil below C star, below the overlap. The overlap's somewhere here. This is entangled. You get nothing out of that measurement, right? So you got to measure the solvent and subtract it. You find out if you do log of the solvent minus of your measurement minus solvent versus concentration, then you're going to find out, oh, there's a magic number. We might plot this phi over phi c, like say this is 1. That would be value 1 then, right? So, or log 0, right? So anyway, so anyway, that gives you a useful thing. You can see this is called Rouse behavior. The viscosity is proportional to the concentration. It's like a linear thing, right? So you have that but Rouse, and you have entangled over here. And in between, that could be called the entanglement concentration more appropriately. Because again, like when you shear, when you're doing a perturbation to the system, you're straightening out the chains. That thing might be significantly larger than the actual unperturbed overlap concentration. Like if you take one chain sitting there, get the size, figure out the mass, that gives you this ratio of those gives you this overlap concentration. But if you stretch that chain out, it's a different story. Like they can easily say you fully stretched it out, it'd be like the length. right? And then it'll be a circle the size of the length. And then that mass, and now there'll be a much lower concentration, right? So, but generally, loosely, it's just said that's the overlap concentration, right? So you'll see, like, I'll show you some other things where you can clearly see this transition, especially polyelectrolytes and stuff, things happen, but this is generally the idea, like why you're doing this, why you take viscosity, why you do that. Then if you take this, so something happens, I'm not sure there's an explanation for this, but if you divide by this solution viscosity, then you find out that this transition not only happens at this thing equals phi star, so the ratio of those is 1, but this thing also, that thing also equals 1 at the transition. So it gives you an idea where to look for this transition. Like, did you go to high enough concentration to get, what was that 1? When that equals 1, that gives you the magic overlap thing. I don't think there's an explanation for why that is, but so basically you're at 2 times the solvent concentration when that thing's 1. Right, that's the idea. So anyway, so anyway, that's why you have this mess here, right? And then there's another part to the story. Okay, this is the other part to the story. So sorry, you have this is just the definition of viscosity. So this is the flow, you have a force going in that direction, and then you're going to say it's being applied to a surface, like a deck of cards. You're pushing the top card, you're sliding it in that way, and it's affecting that surface, the normal to that surface. That's the XY stress, right? That's the shear stress. Then this guy, the strain rate is like a strain, but it's a shear strain. So you're changing it that way, like a deck of cards. You're moving the top card that way, and it's the distance that you travel changes in the Y direction, the opposite direction. So it's a shear strain, right? And shear strain rate, it's the rate of that d dt of that thing, delta Lx over the distance Ly you have, right? So the reason I'm saying this is because those things, you can view this kind of equation, which is called the Einstein equation for viscosity. Einstein said this was they asked him, is there anything you invented that you would wish you hadn't invented, you know? And he said it was this equation, you know? So this is called the Einstein equation. For spheres, this intrinsic number is 2.5 for solid spheres. That's the Einstein equation. Basically, for polymer, that number is significantly larger, right? So anyway, so we'll say like why it is, but basically, if you take that equation, so the Einstein equation with intrinsic viscosity instead of 2.5, so the units, so this is viscosity, that's viscosity. This term 1 is unitless. This term has to be unitless. So that thing's units are inverse concentration, not viscosity. So even though it's called intrinsic viscosity, it's not a viscosity at all. What it is 1 over the overlap concentration. All right, so this thing has nothing to do with viscosity, even though it's called intrinsic viscosity. But anyway, so if you look at that, if you do this at low concentration, which is where you want to do it, so you want to be in that 1 region, which is below overlap. So this is small, concentration is small. So then this term's small. So that means this thing, you can take that and say that's exponential at very small concentration, right? And then if you say that's exponential, and then you can plug this in here for viscosity, and you have exponential, then you have Ly divided by Ly. So this thing times that term, or Ly times the negative of that exponential, like 1 over, right? And then you can re-expand that to 1 minus that. So you can say that effectively you have an effective new Ly because you put stuff in. So you've displaced the fluid, you've taken out, say there were spheres, and then they were floating around, but you could just settle them to the bottom. It doesn't matter if they're floating or settled, because they'll make the Y term in this smaller. It's a displacement function. It just gets rid of some of that space. That means your shear rate, if Ly is smaller, it gets higher, effectively higher, and that gives you a higher torque, right? So this equation, this 1 plus phi n Einstein equation, is basically just a displacement equation. It's saying you put stuff in polymer coils, whatever space the polymer coil displaces, which is C star, 1 over C star, that's going to be removed from your system, and that's going to effectively increase your shear rate. And then that's going to effectively increase, it'll increase your shear stress. Or if you want to look at it, it's just change your viscosity in that way. So the cartoon is this. This is just the displacement law. It's really simple. It only works that way at low concentration, but basically that's where you want to use this. So that's where you get this definition of intrinsic viscosity. You have this term. So if you take your viscosity equation, so is this, then you're going to subtract the solvent, which is the one part, and then solvent times that, so you divide by the solvent. So you have the viscosity minus solvent divided by solvent. That's this guy, right? And then you're going to take it as where the concentration goes to 0. So you're going to limit the concentration. You're going to approach 0 with concentration, and that will give you the intrinsic viscosity, which is just 1 over C star. So it's a way to measure with this like simple machine or that simple machine. You can measure the C star number with it without knowing anything about it, with the twist that the chains are being perturbed in flow, so it isn't exactly C star. So you can kind of determine a lot about the system just from a simple flow measurement. That's kind of the beauty of it. So if that thing's C star, then we can get like the dimension of the chain from that, because we know whatever that is here. Oops, I don't see it here, but basically we know the mass goes with size to the fractal dimension. We know the fractal dimension changes with expanded and collapsed and whatever it is. And from that, we can get basically the structure of the chain from a simple like viscosity measurement here. So Gaussian chain. So this is going to go, this thing's going to give you this law 3 by df. So you can get the fractal dimension of the chain from that this intrinsic viscosity measurement. Right, because it's going to be the volume by the mass, and then the volume is r cubed, and r to the df gives mass. So basically, you can get this equation. You can get the mass from that with this argument to it. So simple measurement, you can get the mass, you can get the intrinsic viscosity, you can get the dimension of the chains in there from just running this viscosity measurement. So this thing, if you just say it's intrinsic is K times molecular weight to the A, that's called the Mark-Hoenk equation, which is Hermann Mark, the guy at Brooklyn Polytech, right? So you can find the Mark-Hoenk coefficients tabulated, like in the Polymer handbook. Basically, you can find A and K terms. Basically, you just Google it. You can find those. The NIST web page has them too. So if you do that intrinsic measurement, you can get the molecular weight using the Mark-Hoenk coefficients. All right. That's it. That's it for today, I guess. Any questions or anything? All right. It's kind of a lot of stuff. Hopefully that's all right. So we don't have McKee on the thing here, whatever it is. So I don't know. Yeah, you can ask him what he's doing. This guy's gone. That's a good question. This thing's called slides 2 second half, but when I was over here, it's called hold on. Let's see. Long range is 2. This is hydrodynamic radius. It's just, but when you open it, it'll be called second half, whatever. Yeah. When you open that, it's called this thing. That's why I was confused. I should change the something there, like put it in here maybe. Yeah. I'm not sure what this one is. I put this up. Oh, that's just a talk. That's a talk. It's not. Yeah, hopefully it's all right. All right. This thing.